There is this thing where everything we've ever known exists within. We call it the universe. We think it existed with what we call the Big Bang. The Big Bang is an expansion from an infinitely small space to something larger. It's followed by what we call the inflation, a brief period that took place right after the Big Bang in which the universe expanded exponentially. The inflation started just 10 to the power of negative 36 seconds after the Big Bang, and it expanded the universe 2 to the power of 100 times until 10 to the power of negative 32 seconds. Despite this extreme expansion, when the inflation ended, the universe was still as small as a grain of sand. It's very hard to imagine how small the universe was before the inflation. We can explain the Big Bang to a degree, but the exact zero moment is still a mystery. We need to be creative to ever hope to understand it, because in the nature, zero and infinity isn't something we come across at all. Perhaps instead of becoming fixed on something from nothing, we could try to imagine something may have always existed. Still, not something easy to think about. We think the universe must have had this inflation period, because without it, we can't see a way for the universe to ever end up the way we see it now. It solves something we call the horizon problem. Without it, the universe could not be homogeneous enough at its beginning to lead to the structures we see today. It also solves flatness problem. The universe we see today is very flat, almost perfectly flat. We also think, due to the quantum mechanical nature of it, once the inflation starts, it may be impossible for it to completely stop. We call this eternal inflation. We think our universe must be only one out of many. And eternal inflation must have started any time before our own universe did. We don't know if eternal inflation had a beginning or not, but we think it must be never ending. We think whenever inflation stops in a patch of space, a universe is created. Through this fractal-like process, infinitely many universes must exist. This idea feels like another step we conveniently add to our definition of existence to explain what we don't know. But the multiverse is only a result of the inflation which we think must be real one way or the other. We haven't intentionally made up of a multiverse. It is a side effect of inflationary expansion. But one concern for the multiverse is it seems to predict everything, and therefore it may not be scientific or testable. And even if it was testable, it would still imply, however crazy it is, anything that could be imagined to definitely exist within the multiverse. Because it implies infinitely many universes. Dragons, fairies, unicorns, anything you imagine must exist somewhere within the multiverse. There are also ideas to reduce the size of the multiverse to a more manageable, finite solution to prevent those implications, and more importantly, to make it testable. But we don't have any experiments ready to test any of that yet. Multiverse also offers a solution to special properties the universe seemingly has. There are several reasons to think the universe we live in may be fine-tuned. One distinct property we see within the universe is the strength differences between the four fundamental forces in the nature. We could imagine, perhaps, the way the universe exists was such an event that it could only cause this universe in this exact way and not in any other way. But we don't have yet a sound explanation for that. So perhaps it's possible there could be all kinds of universes with all kinds of rules, and the one we live in may simply be the one where stars, planets, and life could exist, allowing us to speak these words. Just like life exists on this planet and not in a ton of other planets, these complex structures may exist in this universe because in many others, none of this could happen. It's plain old probabilistic view. We call this idea of the universe the Entropic Principle, or the Entropic Multiverse. The four fundamental forces we see in the nature are gravity, strong nuclear force, weak nuclear force, and electromagnetism. We think at the Big Bang all fundamental forces were united. We think at 10 to the power of minus 43 seconds, the smallest amount of time we can define, gravity was the first force to split from the others. Gravity is the force we're most familiar with. It's the one we discovered the first. It's whatever happens when you jump, when an apple falls, when planets revolve around stars, when moons revolve around planets, and so on. But as we've learned more about these forces, gravity have become more and more mysterious. As inflation started at 10 to the power of minus 36 seconds, strong force also split. Strong force holds the elementary particles we call quarks together to make up protons and neutrons. It also holds those particles together to make up the atomic nuclei. Atomic nuclei with electrons around it make up atoms, which make up all matter, including all living and non-living things. At 10 to the power of negative 12 seconds, or at 1 picosecond, as weak force split, all fundamental forces have become separated for the first time. Weak nuclear force is the reason why atoms decay in what we call radioactivity. A decay means when a particle, for a few reasons, splits into smaller particles. Elements are atoms with different numbers of protons, neutrons, and electrons in them. All elements have the matching number of protons and electrons, but the neutron in them vary. In addition to the varying number of neutrons, when you have both one proton and one electron in an atom, you have hydrogen. With 2, you have helium. With 8, you have oxygen. With 79, you have gold. We've all learned at schools that the same charged particles repel each other, while different charges attract. And protons in an atom are all positively charged, yet they can form atomic nuclei by coming together. Strong force, as the name indicates, is strong enough to hold them together. But even the strong force can only hold so many protons together until they can decay. When protons are numerous enough, they can decay in radioactivity. And so that's why there are only finite number of elements in nature. And that's why more massive elements tend to decay more often than less massive ones. An element can have what we call isotopes. There can be different versions of an element with different number of neutrons, which can affect the likelihood of decay of an atom. Decay is probabilistic. We measure radioactivity with what we call a half-life, which is the amount of time it would take for an element to decay into half of its mass. A half-life can be very short or very long. Whether an element has a stable isotope or not can vary. And the abundancy of isotope also vary from element to element. It simply has to do with how easy it is for particles to come together and stay together or decay. It's a fight between the strong and weak forces. A proton and a neutron are nearly the same mass, but an electron is about 2,000 times lighter. We think the mass difference between these particles also seems fine-tuned. But despite its low mass, an electron is a vital component in electromagnetism in forming chemical bonds. Besides gravity, electromagnetism is the force that is responsible for almost every single interaction of matter we see daily. We also use the word chemistry when describing human relationships, and it's not really the worst analogy at all. Nuclear forces have limited range. They quickly lose strength with distance. Electromagnetism and gravity, on the other hand, do not. Electromagnetism can add up or subtract depending on the charge. Gravity, however, despite being the weakest force of all, is always additive. So with a lot of masses, it becomes more and more noticeable. That's why planets and stars have such a strong gravity. But with small masses, gravity is extremely hard to observe. So fundamentally, it's weak. The difference in strength between fundamental forces are quite strange. If we gave the weak force a value of 1, electromagnetism would be 7,300 times stronger, while the strong force would be 1,000,000 times stronger. Gravity would be 10 to the power of negative 32 times weaker. We don't know why these forces have such a vast difference between them. What we're interested in the most is why gravity is so weak. When the universe was 10 to the power of -6 seconds or 1 microsecond old, quarks were able to form compound particles we call hadrons. Protons and the neutrons are the two most stable hadrons which form a nuclei. A neutron is stable only within the nuclei. It decays into other particles outside the nuclei within 15 minutes. A proton is the only hadron that is stable by itself, or if it ever decays, we think it would take longer than the current age of the universe. As most abundant isotope of hydrogen nuclei consists of a single proton, whenever first hadrons were produced, meant that hydrogen-1 nuclei was produced. Soon after, small amounts of hydrogen-2 and 3 nuclei was also produced. 3 to 20 minutes after the Big Bang, helium nuclei also formed. Almost all of it was helium-4 nuclei, consisting of 2 protons and 2 neutrons. Small amounts of helium-3 nuclei consisting of 2 protons and 1 neutron was also produced. Antimatter was also created at the Big Bang along with ordinary matter at nearly equal amounts, and it started to annihilate when it got into contact with matter, and both turned into energy. Normally, whenever you want to create matter, you create antimatter inevitably, and vice versa, and when they get into contact, they annihilate to turn into pure energy. But at the Big Bang, while both were produced at very similar amounts, somehow there was a little bit more matter. We don't know why this was the case. We call this matter-antimatter asymmetry problem. When the universe was 70,000 years old, there was no more antimatter left, as all of it was annihilated with matter. But 1/10 billionth of excess matter had survived, and this amount of matter was enough for the production of all complexity we see in the universe now. 380,000 years after the Big Bang, the universe became large and cool enough to allow light to pass through space and become visible. Before that, the universe was a hot glowing plasma everywhere. At this point, first atoms finally formed when nuclei have finally combined with electrons. The reason the Big Bang only produced hydrogen, helium, and some lithium is because these are the simplest atoms to form. All the hydrogen in the universe, including all the water that exists, and nearly all of helium is the direct production of the Big Bang. And the way we know all of this is because when we look at the sky, we see the past of the things we look at. This is because, as with anything, light takes time to travel. Light is very fast, but it's not instantaneous by any means. Yet we only really start to notice the effects when we look at the large distances in the sky. There, even the extremely high-speed nature of light falls short. We see the moon 1.3 seconds into the past. We see the sun 8 minutes into the past. The closest neighboring star, Proxima Centauri, is roughly 4 light years away. We see it 4 years into the past. And as we look further and further, we see earlier and earlier. Our closest large neighboring galaxy, Andromeda, is roughly 2.5 million light years away. This is what we call locality. There will always be, no matter how small or large, a delay between interactions. This concerns us if we consider expanding into space, as we eventually should, as Earth will not forever be a place we can live. But at the same time, the fact that light has a finite speed simply allows us to see the past. The speed of light is also related to what we call causality. One thing to cause another, and the future to be different from the past, and not the other way around. Without a speed limit, there would not be such a thing. For light itself, time has no meaning. For it, the time between the Big Bang and right this moment is simply instantaneous. But for anything with mass, time is relative depending on the speed, and all things are subject to causality. When we look at the farthest distances possible, we can see nearly 13.8 billion years ago. Farthest we can see is limited by what we call cosmic microwave background radiation that happened in the year 380,000. But we can still predict fairly well what happened before that time using that data. Many of the information we have about the universe and its first moments are gathered from that. 1% of white noise we get from TVs and radios are from this radiation. It is now in microwave because it has stretched from higher wavelengths to microwave as it traveled for nearly 13.8 billion years. We see it very, very uniformly across the whole sky, and this is how we know it is an afterglow of the Big Bang and not caused by something else. First stars and galaxies in the universe took hundreds of million years to form. Yet this amount of time is still somewhat a brief moment in the lifetime of the universe. But to understand how stars and galaxies have formed, we first have to understand two more concepts. In the recent years, we have found out that there is a force that accelerates the expansion of the universe. We call that dark energy because we don't fully know what it is. We think it's the energy of the vacuum itself, so whenever new space is created from the expansion of space, we think this energy is created along with it at the same rate, so it keeps on accelerating the expansion. Dark matter, on the other hand, is almost the exact opposite. We think dark matter is a type of matter that doesn't interact with any fundamental forces other than gravity. It only causes gravity. In a way, it could be thought of as a glue. Based on our observations and calculations, without it, even if they formed somehow, galaxies would not have remained together. We have searched for alternatives and explanations for both, but we are pretty sure they exist as discrete concepts and they're not a result of something we already know. We know a little bit more about dark matter. We have a few candidates for it, and we may soon discover what it really is, but dark energy is a little bit more mysterious. We think, as of our recent observations, dark energy make up about 68% of the universe, dark matter about 27%, and ordinary matter that makes up everything we can really see makes up only 5% of the universe. Thousands of years after the Big Bang, the universe was still expanding, but it was slowing down due to gravity caused by matter and dark matter. However, when the universe was about 5 billion years old, it had finally reached to a point where it was large enough for dark energy to overcome gravity and accelerate the expansion. We think for the last 9 billion years, the universe is expanding in an accelerating rate. We think it is currently expanding faster than the speed of light, likely much, much faster. The universe can expand in such a way because the space itself isn't bound by the speed of light. This is why we have a concept we call the Observable Universe. Due to the limited speed of light, there is a limit to the universe we can really see from the whole. As the universe expands faster and faster, we can never, ever hope to see beyond the observable universe, beyond our cosmological horizon. Gravity caused by matter and dark matter is what keeps matter together to form stars, planets, and galaxies. Gravity is one of the most important factors for complexity, structure, and life to form in the universe. When the universe was expanding slower, and when matter and dark matter was denser in space, it was a little bit more easier for structures to form. We think mostly with the help of dark matter, a sort of broad structure was formed throughout space we call the cosmic web. This helped matter to clump more in areas where dark matter was concentrated. When the universe was about 100 to 150 million years old, first stars have formed. At this point, most of the ordinary matter in the universe was still hydrogen and helium. The first stars were made up of only these two gas elements. Stars are one of the most important objects in creation of complexity in the universe. Stars form whenever there is enough amount of matter in a region of space to slowly coalesce due to gravity. When gravity is strong enough, something we call nuclear fusion happens to merge atoms together to form heavier ones. In the process, energy is released in the form of light. Stars not only do produce energy, but also in a few ways create nearly all of the other elements that was not created in the Big Bang. Some elements such as lithium, carbon, nitrogen form inside low-mass stars. Many elements such as sodium, aluminum, oxygen, and iron form whenever massive stars explode in what we call a supernova. Less massive exploding dead stars, what we call white dwarfs, also create some of iron and nickel in the universe. And more than the others, many of heavier elements form when another type of dead star, what we call neutron stars, merge. We not only think stars have formed when the universe was this young, we've also physically observed some of them. And some of the oldest galaxies we have detected were formed when the universe was only 400 million years old. Galaxies are groups of billions of stars that are gravitationally bound. They rotate around their own center. In the center, however, lies something strange. When we look at a spiral galaxy from afar, we see a bright center which is made out of millions of stars that are actually not that close. What's in the exact center could be considered the demonstration of gravity reaching to the extreme. We have to note that every star has a beginning, a main sequence, and an end. A star is considered a star as long as it maintains fusion and radiates light as a result. When fusion stops, a star can either have a slow end by turning into a white dwarf or a neutron star, or it can die by exploding in a supernova and leave behind what we call a black hole. A black hole is a sort of a dent in space-time, a three-dimensional hole, if you will. It's spherical, yet it's a point-like object, and the gravity is the strongest within it. Imagine taking any object inside your hands and squeezing it until you can't anymore. Imagine you put all the mass you can find on top of it to compress it even more. A black hole is what happens when an object is compressed to the absolute maximum. Technically, any mass can be made into a black hole. It would have a much smaller diameter than the original matter it's used for it to be made, but it would be a black hole. The mass of the matter is what determines the size of the black hole. In a star evolution, a black hole can only form if an object is as massive as 3 times the sun's mass. Only then a star would generate enough gravity at its depth to collapse in on itself. A black hole is black because its gravity is so high in the center. The speed required to escape its pull becomes greater than the speed of light. And as nothing can travel faster than the speed of light, whether light or any other matter, anything that falls within its inescapable range we call the event horizon can never leave. And as light can't leave it, it can't be visible. The only way to see a black hole is to see the orbiting light and matter just outside of its event horizon. But black holes aren't perfectly black because they radiate nothing but one thing, and that's how they eventually die. We call this Hawking radiation, and the way it works doesn't contradict with what happens when you cross the event horizon. Hawking radiation happens just at the edge of the horizon, when pairs of particles we call virtual particles that are momentarily created and destroyed are separated by this horizon. One of the particles enters the black hole and the other leaves without entering. And this separation causes virtual particles to become real particles and cause a black hole to lose its mass very, very slowly but steadily. As it is so slow, it takes very, very long time for black holes to evaporate and die, but they eventually do. And in the center of galaxies lie what we call a supermassive black hole. These black holes are millions to billions of solar masses. They are made out of countless stars that turned into black holes and gradually merged and ended up in the center. When first stars formed, there were more mass density in space, and therefore it was possible for more massive stars to form. But with more mass, stars burn their hydrogen and helium faster due to higher gravity, and they start to fuse heavier elements faster. However, a star can only fuse elements up to iron. When they reach iron, they lose energy instead of producing it, and so they cannot provide energy to sustain the balance against gravity. And this causes a star to collapse. So those early massive stars are all black holes now, but they have in their supernova scattered all the heavy elements they created across the space. Without these heavy elements, most of the structures we see in the universe, planets and life, would never have formed. The best place for planets and for life is within galaxies. We don't know if ever life existed or will ever exist outside a galaxy, but simply a galaxy allows for matter diversity and more chances for creation of life. Our galaxy is thought to have formed 600 million years after the Big Bang. It's 13.2 billion years old. Our Sun, however, is much younger than that. It's 4.6 billion years old. The Earth follows it closely at 4.5 billion years. The Sun is not a very massive star, but also not one of the smallest. Most of the stars in the universe are red dwarfs, which are low mass in their main sequence. They're the smallest possible stars that can maintain fusion, and so they have the longest lifetime out of all. In fact, no red dwarf have ever died in the universe so far, assuming it didn't interact with another massive object. The biggest stars, on the other hand, live only a few million years, so they aren't the most common ones simply because they last a whim. And as the universe ages, they will be less and less common. Our Sun lives an average life compared to the two extremes. At the age of 4.6 billion years, the Sun has around the same amount of time left to live. But long before the Sun expands to turn into a red giant and eventually turn into a white dwarf, in about 500 million to 1 billion years, the Sun will become hot enough to make the Earth uninhabitable for life. The largest stars don't allow enough time for life to evolve. The smallest ones have a lot of life in them, but they're not a great place either, because the planets around them need to be a lot closer to their star to be habitable, and red dwarfs are usually a lot more volatile stars than slightly bigger stars. Stars like our Sun, while aren't as common as red dwarfs, are still quite common within the universe, and so there's plenty of chance for life to emerge elsewhere. There are a few other reasons that help life to emerge on Earth. We have quite a big moon relative to our planet. When we look at the other planets in our solar system and in other systems, we don't see that often. And the way it was formed may not be a very common event. We think a Mars-sized planet hit Earth, and some of the debris merged with the Earth, while the remaining formed the moon. The existence of moon helps stabilize our planet's axial tilt, and this feature may have been crucial for evolution of life on Earth. During its first few 100 million years after its formation, Earth was a hot volcanic place, and for a while it was bombarded with asteroids and comets. First life on Earth did not take too long to emerge, but multicellular life did take some time. Early simple life on Earth did not use oxygen, but when photosynthetic life emerged and filled the atmosphere with oxygen, most life that lived before that went extinct. We think first plant life have emerged about 850 million years ago. We think first animal life emerged about 600 million years ago. Eventually, around 540 million years ago, something we call Cambrian Explosion happened, where organisms have rapidly diversified in a relatively short time. Life on Earth was quick to start, but late to evolve into the higher complexity we see today. There are several events in the history of the Earth where we see mass extinctions within the last 500 million years. We know from the fossil records at least 5 times on Earth, life have become extinct to a degree ranging from 70% to 90% of all life. And despite that, life still managed to survive to this day. One of the extinctions that wiped out dinosaurs from the face of the Earth happened 65 million years ago, and we think it was caused by a meteor that hit Earth. Only 500,000 years ago, archaic humans, and about 200,000 years ago, anatomically modern humans have finally evolved. So far, aside from our extinct cousins, we are the only intelligent life we know in the universe. Life may be common within the universe, but complex life may be harder to come by, and intelligence even harder. But considering the vast possibilities, it's very likely to imagine we're not alone in the universe.